Good afternoon, General Chemistry. We're picking up, starting our new chapter on oxidation and reduction reactions. So in class, you've already started learning about this. So these notes are just to help you have something in your notes to look back on and refer to, and also to practice what we've been learning in class. So the overview of this chapter, we started by learning about what reduction and oxidation mean. We started looking at some redox reactions. We're going to look at activity series, and then we're going to end by talking about batteries, how redox reactions apply to our everyday lives. We did this concept map, so I'm going to run through this quick. We talked about it in class. So if you never filled in this concept map, take a second to do that. I asked you to go through and look at some of these review terms, define them because we're going to be using them again. Let's pick up then oxidation and reduction. So you did a packet where you looked at a reaction in real life and then you got to see a model of that reaction. Reduction happens when something gains an electron. So reduction is gaining of electrons. When an element gains a negative electron, they say it's been reduced. So if something's been reduced, it's gained electrons. And here's that example. We have iron 3 plus an electron gives us iron 2 plus. So this iron is being reduced here. Oxidation is the removal of electrons. And it says when elements lose an electron, we say it's oxidized. So it's oxidized, its charge goes from +1 to +2 because it's losing an electron. Now, one of the things in the packet that I mentioned is even though we say something is reduced when it gains an electron, the charge is what's changing. This oxidation number is being reduced. So it's going from +3 to +2. So the charge is going down. That's why we say it's being reduced. Where here, oxidation, the charge is going up. Okay? But those are terms you need to keep clear. And we use the acronym LEO goes GER. LEO, LEO stands for lose electron oxidized, and GER, gain electron reduced. Okay, so that's in your packet that you're getting back today. So let's talk about them happening. They have to happen at the same time because it's a transfer of electrons. So you cannot have reduction without oxidation. When one element is reduced, the other is oxidized. It happens at the same time. The complete process is called redox reaction. So it's just an abbreviation of reduction and oxidation. We just say redox. In a redox reaction, you have to balance both the charge and the atoms. So this is where being able to assign oxidation numbers come in. We have to keep track of where the electrons are moving and overall balancing of the equation. So this is going to draw on what we learned in previous chapters. So here's an example. Rust is a good example of an oxidation reaction. Okay, we have iron reacting with oxygen to make rust. And we're going to talk about how do we tell who's getting the electron and who's giving the electron. Okay, but that's an example of a redox reaction. So first, determining oxidation numbers. We've talked about in this class. We're going to talk about it some more. So first of all, an oxidation number is the apparent charge of an atom when lone pairs of bonding electrons are assigned to it. We use oxidation numbers to keep track of electrons in a redox reaction. So in a redox reaction, we're saying we are talking about apparently where are the electrons. So it's not always going to make perfect sense, but it's just a set of rules to let us figure out what's oxidized, what's reduced. So I have C handout on rules for oxidation states. So I handed you out in class a yellow rules for oxidation state sheet. And when we say oxidation state, we mean numbers. It's the same thing. So you need to have that out in front of you. If you don't have that out in front of you, get it now. You can pause the video, go get that out in front of you. And we're going to do some examples for assigning oxidation numbers. We switch to a pen. Let's do purple. Okay. So for assigning oxidation numbers inside a compound, always start with what you know. So if you go and look through, you look at number 3 on your rules sheet, it says certain elements when present in compounds form common oxidation. So 3A on your rules says that alkali metals, and it says sodium in there, are always going to be +1. So based on that rule, we know that sodium is going to have an oxidation number of +1. Chlorine, then, because the overall charge of the atom has to be 0, then if sodium is +1, chlorine is going to be -1. We also have a rule, letter E, that says the halogens are -1. But these two numbers, so +1, if we add it to -1, are going to equal 0. So overall, the charge is neutral on a molecule. Here then, also in number 3, we're going to start with oxygen. So oxygen, if you look at your rules, 3D, says oxygen is -2 when it's in a compound. So that means each oxygen is going to be worth -2. So that's each. So if each oxygen is worth -2, that's a total of a -4 charge. So 2 times -2 gives us -4. That means carbon, if the overall molecule is going to be neutral and equal 0, then carbon must be +4. Right? So you start with the ones you know based on the rules, and then you can figure out the ones you don't know. So here we have a big one. Okay, we got sodium. So we can do sodium, and we have to figure out sulfur and oxygen. All right, and we know they're different elements because of the capital letters. So sodium, when it's in a compound, always going to have a +1. In this case, we have 2 of them, so I'm going to put each. So it's +1 each. So because there's 2 of them, that's a total of +2 total, because we have 2 sodiums. Then sulfur. I'm not sure about sulfur yet. There's no rule for sulfur. So let's jump to oxygens. We know the oxygens are always going to be worth -2 each. So 2 times 4, -2 times 4 is going to be -8. So that's how much charge oxygen is bringing. So if we look, sodium brings a total of +2 to the compound. Oxygen brings a total of -8. So if we want it to equal 0, sulfur must be +6. And we only have one of them, so it's just +6 for each sulfur. Okay, so then these are our oxidation numbers for each element in the compound. All right. So that's how you assign oxidation numbers, and we did a lot of practice with this in class, so hopefully you're able to master this skill. Next, identifying what element has been reduced and oxidized in each reaction. So the first, oxidation numbers must be determined for each element on both sides of the reaction. Next, look to see which element was reduced, so which gained electrons and which was oxidized, which lost electrons. And let's do an example. So I'm going to switch to let's do a red pointer this time. So first of all, I'm going to ignore these coefficients. Just ignore them. You don't need to worry about them yet. So strontium, okay, free element, it's not bonded to everything, so its charge is going to be 0. Oxygen, O2, free element, not bonded into anything, so it's going to be 0. Let's go over here. Now we have a compound. Start with what we know. Oxygen always is going to be a -2 when it's in a compound. So if overall the charge of this compound is neutral, then strontium must be +2. Okay, so now we need to look at which one was reduced and which one was oxidized. So let's look at strontium first, Sr. It went from 0 to +2. So if it goes from 0 to +2, that means it must have gained electrons. Or sorry, not gained electrons. It lost electrons, so it was oxidized. I can also tell because the oxidation number, has gone up. It went from 0 to +2, so it must have been oxidized. Oxygen, so the O2 went from 0 to -2, so it gained electrons, and its oxidation number went down, so it was reduced. Okay, so you have to always start by assigning those numbers and going from there. So I think I have another example. I do. So let's get a pointer. And I'll do, I think I'm always in purple now. That's right. So first, start by assigning oxidation numbers. So lithium by itself, not bonded to anything, going to be 0. Sulfur again, by itself, not bonded to anything, is going to be 0. Now let's start with what we know in this equation. Lithium, it's an alkali metal. If we look, alkali metals usually have a +1 charge. So each lithium gets a +1 charge, +1 each. There's 2 of them, so overall we're getting a +2 charge from the lithium. So sulfur, if this whole thing is going to equal 0, sulfur must be -2 in this case. So then we look, lithium went from a 0 to a +1. Sulfur went from a 0 to a -2. So lithium, sulfur, in this case lithium, lost an electron, oxidation number went up, so it was oxidized. Okay, and then sulfur went from 0 to -2, so it was reduced. It gained an electron, or it actually gained 2 electrons. All right, do I have another one? I do have one more, so let me get rid of some of this stuff in the way. There we go. Okay, so again, start by assigning oxidation numbers. So chlorine, Cl2 by itself is not in a compound, so it's going to be 0. Here we have a compound, so start with what we know. Sodium is an alkali metal, so it's always going to be +1. Bromide is a halogen, has to be -1, so +1 and -1 are going to equal 0, so that's neutraled out. Remember, I'm not going to worry about these coefficients. Don't worry about the numbers in front. So then chlorine, -1, sodium, +1. Bromine by itself, it's not bonded to anything, it's just hanging out with other bromides, so we're going to say it's 0. So now we need to look. I noticed that chlorine, Cl, went from 0 to -1. Notice that sodium didn't change, stayed +1, so it's not changing. Then bromide went from -1 to 0. So what was oxidized, what was reduced? So I'm going to start with chlorine. We say it went from 0 to -1, so it was reduced. And then bromide went from -1 to 0, so its number went up. It was oxidized, it lost an electron. All right, so hopefully that makes it clear on how we determine what's being oxidized, what's being reduced in a reaction. And that's where we're going to stop for today. We're not going to go any further than that. So I hope this helped. I hope you feel like you can now assign oxidation numbers and determine what's being oxidized and what's not. All right, we'll see you in class.